about solubility product, and that's just a fancy way of talking about a different type of equilibrium. Now, one of the horrible truths that I'm going to share with you right now is this. You guys remember when can you guys hear me okay? Can I get a thumbs up if I'm coming in all right? Okay. So one of the things that we learned a while back were solubility rules. Remember the NAGSAG rules, A, B, C, D, blah, blah, blah. And we said definitively, these are some things that are soluble. These are some things that are insoluble. And if you take a look at calcium oxalate up on the board, can you put a finger on the left-hand side? That right there, calcium oxalate, if we went through the NAGSAG rules, or A, B, C, D, no rules would be able to be applied until we got to the second part of the, stay over, keep your finger on that still. No rules would be able to be applied to that. If you went through the NAGSAG rules, it's not a nitrate, it's not ammonium, it's not acetate, blah, 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 blah. But the second part of the NAGSAG rules were, if you can apply any rules, then the -2s and the -3s are insoluble and -1s are soluble. And in this case, oxalate is a -2. Agree? Thumbs up if you agree with me on that. You should, because I'm telling you the truth. Okay? Well, good. I appreciate the affirmation. So by all definitions, calcium oxalate should be insoluble, which means it does not dissolve in water. Now, let me remind you of a quandary we're now facing. Hey, mi amor, can you grab this here? Because he's getting ready to slap with his hands. My son is enjoying pillows right now. I don't know if you can see him. Maybe you can, maybe you can't. Did you see? Harrison, ¿qué estás haciendo?
Dile hola.
Dile hola.
Los niños.
Hola. You guys see him or no? Well, that's my son. And I may have to let me put on these. We may have to move him out of the way because his cuteness is melting me right now. All right. So yeah. So back to the exciting world of solubility. So the reality is that calcium oxalate should not dissolve, and all of the things that we said based on the NAGSAG rules are insoluble. Here's the lie. Even the worst insoluble thing dissolves just a little bit, just a tiny bit. So calcium oxalate, if you take a look, we've drawn a double arrow up above, which represents an equilibrium, which means that some of the calcium oxalate will dissolve and form Ca2 plus and C2O42 minus. Now, note something here. She wrote the KSP, and if you're wondering, like, what does KSP mean? Well, SP is just the subscript that allows us to let us know that we're dealing with a something that does not dissolve or does not dissolve very well, but don't be frightened by it. But it's just a regular K. So in our K expressions, don't we always include those things that are aqueous and gases, but not things that are liquid or solid? And so as she wrote on the board there, that we did not put CaC2O4 on the bottom because, well, why, right? So that is our equilibrium expression. So let's go to some statements here. Can you guys open up your notes? I'm gonna screen share just for a moment and go to my okay. Oops. Okay.
It's
so
presenting on me.
Can you? Is it still presenting on you?
Yeah.
Okay. Is it? I'm guessing you can see it now. Okay. All right. Thank you. So, solubility product constant KSP is when we have very slightly soluble or almost insoluble ionic compounds. And in this case here, when we looked at our rules, we said that CaC2O4 should be insoluble. So when it actually forms an equilibrium, we call those equilibriums KSPs. So don't be frightened by it. It's just a way of saying that we're dealing with something at equilibrium that doesn't really want to dissolve, which would mean that if we looked at our Ks, our K value should be really, really low because not very much stuff goes to the product side. Now, just to remind yourself of a few things here, when a solid is first added to water, no ions are present, but as the dissolution proceeds, the concentration of the ions increases, making it more and more likely these ions will collide and reform the solid phase, this is how equilibrium is formed. So the reality is this: we start off with only, and I don't know if you can you guys see, can you see the little mouse moving around here? You're gonna have to answer for the class.
Yes.
Okay, so if we just throw CaC2O4 in water, right? We just throw it into water. At first, some of the particles are going to jump over and form Ca2 and C2O4. But as more and more of the Ca2 and C2O4s, 2 minuses, are formed, they're going to hit into each other and they're going to reform CaC2O4, and they're going to form an equilibrium just like any other equilibrium would, except for the fact that this is not included in our concentrations in our equilibrium expression. It is a solid. It does not matter how much solid we have. So if I put a little pebble of CaC2O4 in water, or I put a huge chunk, the amount of Ca2 plus times the C2O4 as represented by this equation will be always equal to the same amount of KSP. And they did not give you the KSP for this problem. We'll come back to that in a little bit. Once this equilibrium is reached, no more solid dissolves. That's whatever. But this bottom portion right here, this last bullet point, is actually really, really important. Increasing the surface area of the solid, adding more solid, and stirring up the solution all will help you get to equilibrium faster, but none of these will shift the equilibrium. For example, if we double the surface area, we also double the rate at which the solid reforms. So the only thing that we are worried about is that the KSP tells us how much of the Ca2 plus and C2O4 2 minus were actually allowed in solution. Now, let's do this problem here on the board, if you wouldn't mind. Can you write the formula PbI2? Just write that as it is, and then I'll go to it. And if you can write next to it, erase everything that's on the board right now and just put this on the top here. We have 1.2 times 10 to the negative 3 moles of lead-2 iodide dissolves in 1 liter of aqueous solution. Now, in spite of, I know that you guys have this stuff down below that you can always see how I work through this, but for right now, I want you to just kind of pretend that you don't have that so you can walk through the steps with me.
So.
Okay, coming back to you here on the board. I'm going to stop screen share, and I'm going to go to Kirsten. Just do a 1 liter of solution. Okay, so one of the things that we're going to talk about here in a little bit is solubility. Solubility is really how much of the solid dissolves. Can you put your finger on the PbI2? So would you acknowledge that for every X that leaves PbI2, won't I gain an X for Pb2 plus? Put your finger on Pb2 plus. And won't I gain 2X for the I minus? So let's say I were to tell you this. I tell you that I lose, put your finger back on PbI2. Let's say I told you that I lost 2 molar of PbI2. We can't say molar because it's not concentrated, but let's say I lost 2 moles per liter, right? That's why they wrote it. Do you guys realize that that's why they wrote it as, oh man, 1.2 moles of, this is problematic. Okay. I have on the top of my screen is the little thing that allows you to shut down, and every time that I move my mouse, it appears and it covers up what you've written up above. So I'm just not going to move it. So if you were to take a look at this, and I were to tell you I have 2 moles per liter of PbI2 are leaving, wouldn't that mean, since it's a 1-to-1 ratio between the PbI2 and the Pb2 plus, wouldn't I gain 2 moles per liter of that? And since it's a 1-to-2 ratio between the PbI2 and the 2I minus, would you agree that I'd gain 4 moles per liter on that? So one of the things we're really doing is we're really just solving an ice problem. But that original amount, can you put your finger up there on the 1.2 times 10 to the negative 3? Okay. That is our solubility, and solubility equals X. So can you put like an arrow down and go, put an arrow down to it and go solubility. If you want to say solubility equals X. And you can equals also, I'm hearing echo right now. Did someone unmute?
No, I think it's just the speakers.
Okay. And that's equal to, and you can put it in molar, capital M, which is equal to moles per liter. So one of the things we often say is when we talk about solubility or X, we talk about molar solubility. So in this particular case, they tell us that we have our solubility is 1.2 times 10 to the negative 3 molar. Would you agree with me that that's the amount of that goes into solution?
Yes.
So if that goes into solution, would you agree with me if we call that X? So initially, let's just do this. Let's do an ICE just because we can. Okay. And can you put 0 and 0 for the PB2 plus and the 2I minus? Now, notice how I'm not going to put any concentration with the PBI2 because we don't know, there is no initial concentration because it's a solid. But the change is going to be, don't we lose X? And don't we gain X? And don't we gain 2X? And then at equilibrium, don't we have, ignore the first thing because we don't put a line through there. No. We cannot. Yeah, sorry. This is why I kind of was hesitant to put minus X on that side there because it's a solid. It doesn't ever enter an equilibrium. It's not part of equilibrium expression. So can you write over underneath PB2 plus, can you write X?
Right here.
PB2 plus.
Oh.
Write X and write 2X. You guys may have to take me off of speaker because if I'm hearing that loop, it's probably going to play on the video as well.
Okay.
Everyone else, if you can plug in your headphones. Okay, are we good here? Yeah, that got rid of it. Thank you. So one of the things that they're asking in this problem is they're asking, what is the KSP for this reaction? They give us the X or the solubility, and they ask for the KSP. So can you write the KSP expression for this, please, underneath?
Right here?
Yes, please. Okay, now we know what the X values are, right? So let's plug those X values in. Would you agree with me that it's going to be X? And then it's going to be 2X squared. And that's going to give us as equal KSP. And then is that going to be equal to 4X cubed? Is equal to KSP. Now, I'm doing this a little bit differently than your notes because I want you to get used to what X means. I need you somewhere, anywhere on your page, see up above where it says solubility equals X. Can you like box that and like star it or make it in a different color or put it somewhere because solubility is always X. So when they talk about how much dissolves from the original, that's your solubility and that's your X. So in this case, you see how they gave you 1.2 times 10 to the negative 3 moles. Now here's what's important. They have to tell you how many liters that's dissolved in, right? So they're gentle because they gave you 1 liter. So 1.2 times 10 to the negative 3 in 1 liter is going to give you 1.2 times 10 to the negative 3 molar. That is your X value. If you know your X value, couldn't you just plug that in for your X right there? And couldn't you solve for your KSP? Can someone plug that into your calculator and spit that back for us, please? Okay, so let's just we don't have to worry about the units right now. So if we took a look at that, 6.9 times 10 to the negative, remember we told you that equilibrium constants we can get away with not writing units ever. Take a look at that, 6.9 times 10 to the negative 9. Isn't that an incredibly small K value? In essence, doesn't that mean, if you're just trying to analyze it, doesn't that mean that almost all of it stays as PBI2 and only if you multiplied the PB2 plus concentration, can you put your finger on the KSP expression right there at the very top? This right there. Put your finger on the PB2 plus and the I minus. Okay, if you were to multiply the amount of PB2 plus and the I minus that you're allowed in solution, in any solution, the number has to be 6.9 times 10 to the negative 9. So how much PB2 plus and I minus ions really do come off of the PBI2? Wouldn't it have to be an extremely small amount?
Yes.
I mean, if we're comparing essentially times 10 to the 9th, isn't that a billionth? So you're essentially going to end up with 1 billion times more PBI2 than you have PB2 plus and ion minus. That's a pretty significant, can I restate that? That is not very much being dissolved. So in reality, we didn't say it was insoluble, because we said it was insoluble originally, but if only 1 billionth approximately of your solid dissolves, that's pretty darn close to insoluble. So we call this slightly soluble, and that's why we call it a KSP instead of a K. Any questions so far? Now, time and again, what they're going to do is they're going to give you the solubility. Now they'll give you the molar solubility, or sometimes they'll give you the solubility in grams per liter. Now, think about this for a second. If they give you the solubility in grams per liter, and X is solubility in moles per liter, what do we have to do?
Grams and then
And I love, that's awesome. So what she did is she, as I reenact for those of you who can actually see, if you have grams, you can't use the periodic table and the molar mass of whatever you're dealing with to get to moles.
yeah.
Right? So if you have that, then you can convert to moles, and then you get to molar mass. I'm sorry, then you get to the molar solubility. Okay, so we can start with the solubility, X, and work backwards to the KSP. Or we can go the other way around. We can start with the KSP and work forwards to our solubility. So let's do that right now. And let's do the problem that we actually see in the notes, which is the next problem here. And I'm going to, if you can write the CAF2 thing down on the board.
Where?
I'm going to, it's the next, scroll down to the next little part where it says CAF2.
Oh, okay.
Okay, I'm going to start screen sharing just so you guys can work along with me. By the way, your homework for tomorrow is the homework that I gave you from the textbook from before. Remember, I told you that that needed to be done. That was done last class period. The homework for today was actually the titration worksheet that you were supposed to do. I have not checked it because we have a very small class time, but we will go to that. Yeah, go to that tomorrow or Thursday whenever we have class. Okay, let me jump to the actual worksheet. So, by the way, I was deliberate in giving you a when we used the PBI2 example. I wanted to give you an example where we didn't have a 1-to-1 ratio, just so you can see that it impacts us both the square right here, and then when we're dealing with the X. Now, what I'm just talking about right now, what we're going to do is we're going to flip the problem around, and we're going to do this. We're going to calculate the solubility, and look at that. Look at the meanness of that. You guys see how it's in grams per liter they're asking for?
Yeah.
Of the calcium fluoride in water, and they're going to give us a solubility product of 3.4 times 10 to the negative 11, which again is a wickedly small KSP. On the board, I'm assuming that you've written this right here, correct? CaF2 goes to Ca2 plus F2F minus?
Yes.
Okay, wonderful. Thank you, Kristen. I'm going to stop presenting. I'm going to go back to Kristen on the board. And in the future, can you just write a little bit lower on the, actually, can you tilt my screen up just a little bit? Perfect. That's perfect. Wonderful. Okay, are you seeing yourself on the screen right now?
Yes.
Okay. So what they're doing in this case here is they're giving us the KSP and they're asking us to solve for the solubility, aka they're asking us to solve for X. So what do? Well, let's do an ice problem up above. Brilliant. And the reality is most times when they do an ice problem, they don't do anything with the CAF2, but I like having the change be a minus X so you can see where we got the minus X from. So then let's write the law of mass action with KSP, please. And then let's plug in the X values that we got, that we were given. You're gonna quickly notice a couple things. If you ever have just an X and an X, your KSP is always going to be X squared. If you ever have one thing to the or the coefficient of the 2 is going to be 4x cubed. They can get more complex, but in this case, it's 4x cubed. Agree?
Yes.
So all we're trying to do is solve for x. Don't they give us the KSP value?
Yes.
Can we put 3.4 times 10 to the negative 11 in the place of the KSP? And then equal to 4x cubed? That's what I meant to say. Because we're trying to solve for the x. And can we isolate? So we have to divide that by 4. And then you have to take the cube root of it. Brian, that works. I just saw your thing on the side, your chat. Can someone punch that in a calculator? And by someone, I mean everyone.
What color? We got it.
What's the number?
2.0 times 10 to the negative 4
Okay, that's equal to x. What did they ask you to solve for in the problem?
grams per liter.
Okay, so can you put right there equals x equals, can you write next to the 10 to the negative 4, can you write molar? Yeah. So right next to the x, where the 2.0 times 10 to the negative 4, can you put a capital M next to the 2.0 times 10 to the negative 4 as the unit?
Yeah, so like under it.
Well, yeah, I mean, typically when we do it, we write right on the end of that, right before the equal sign, we write an M to make sure that everyone understood that the 2.0 times 10 to the negative 4 was a molar amount. And then write equals x. Perfect. So that we don't have to write the other stuff. Now, this is the main thing, and they did this a few years back on the AP exam, is they asked for the solubility in grams. And so students, almost all students, what they did is they solved to this x, and they left the problem. But if they're solving right now to this x, that is the solubility, the molar solubility, or in moles per liter. We have to go one step farther, don't we?
Yes.
We got to go to grams. So in this case right here, isn't 2.0 times 10 to the negative 4, isn't that the same as saying 2.0 times 10 to the negative 4 moles per 1 liter?
Yes.
So can you write that up like in a table? So put that in the upper left-hand corner of a table. 10 to the negative 4, and then write moles on the top, and then put a line and put liter on the bottom. Right? And then then write 1 mole of CaF2 on the bottom, and then write grams of CaF2 on the top. And we have to figure out what the molar mass is of the CaF2.
Is 40 and then F is 19 about. And then what's?
And if you notice here, see what cancels? The moles cancel, and now we know what our grams per liter are.
Zero 0.0159 grams per liter.
That's wonderful. So let me lock this in. You know how when we were dealing with problem before, I'm like, hey, you have an acid or base, and you know what to do, what you do with it, and you like, the stimulus response was like, throw it into water. Well, here's you're gonna do the same thing. Whenever I ask you what is solubility, you're always gonna say what?
Equals X.
X, always. Solubility equals X. It doesn't matter how complex your problem is. It doesn't matter if you have, 4x cubed or whatever else. No, you throw only acid and base into water, Cody. Here, solubility equals X. You do not throw solubility into water. Although that is clever. And I love the all caps because it tells me you mean business. So take a look at that for just a second, and will you acknowledge that this is not really any different than the problems we've been doing? I mean, the only thing different is that you don't have a reactant because it's a solid. And 2, you have to acknowledge always that they're going to give you solubilities, and the solubilities are molar solubilities, and that's equal to X. Now, one of the things that they're going to do in the next section, and this actually becomes quite challenging mentally, is they'll throw 2 different compounds into water, and then they'll ask which one of them precipitates first, and then they'll ask how much precipitates, and those problems can become a little more complex. So let's just make sure that we have a sound grasp on this. And let's go back to the worksheet, if we would. I'm going to screen share myself again. How much time do we have left? Like 7 minutes?
Yeah.
5, 7 minutes? Okay.
Yeah, about.
Okay. So you guys are seeing my screen right now again, Kristen?
Yeah.
Okay, wonderful. Okay. Let's do one more problem. Let's do number 3. I want you all to do this on your own. You can do this on the board. Do not look at the answer. In fact, why don't you do this, Kirsten? Just write this problem on the board, and then everyone else stop looking at the sheet so you can do it on your own. I want you to practice on it just to make sure that you feel comfortable with it.
Okay. Wait, do this problem on the board?
So problem number 3, yeah, just write the KSP for copper 2 iodate is 1.4 times 10 to the negative 5. Calculate solubility. By the way, see how it's writing 25 degrees Celsius, and they're making that point to tell you it's at 25 degrees Celsius. That's because temperature changes your K. So it doesn't impact our problem in any way because they're giving you the information that you need. But if they gave you something at 25 degrees and the KSP of the same thing at 50 degrees, those would not be the same KSPs. Temperature changes your K. So you're writing that on the board right now?
Yes.
Okay. So everyone right now in the next 2 minutes, I want you to solve that problem. Don't skip steps because I know that some of you guys are clever and you're going to jump to the fact that, oh, wait a second, that's a 4x cubed, which I probably shouldn't have said out loud, but yeah. I'm hoping you guys are all doing this simultaneously with her. I'm showing right now on the board. Kristen back again.
3.3 times what? And is it asking for it?
Asking for the molar solubility, I think, correct?
I think so. Yeah.
Okay. I've given you guys 3 other worksheets of things that are online. I'm going to share my screen again. I did not have them printed out with you, but any questions on what I've just shown you so far?
No.
It's pretty straightforward. Anyone in the class? Okay.
No.
All good? Okay, let me screen share again. And stop presenting. So if you look here, there's 3 different, 4 different worksheets right here. If you go to relative solubilities, so let's take a look at this here for just a second. I'm gonna make this a little bit bigger. Kirsten, can you verify that you guys can see what I have on my screen?
Yes.
Okay, so solubility is X, right?
Yes.
So we can compare 2 things, their KSPs, as long as the formula for the solubility product is the same. So if I looked at AGI and CUI, right, and all 3 of these right here, and if you notice these, don't these all break apart into 2 particles only?
Yes.
So wouldn't that give me at my equation? Wouldn't that give me KSP is equal to X squared?
Yes.
So if I did that and I solved for X, wouldn't the ratio of these right here allow us to determine which one of these probably is more soluble just based on the KSP?
Yeah.
So if I looked at these three here, would you acknowledge that the CaSO4 is clearly the most soluble of these three if they all break into the same number of particles?
Yes.
Everyone with her? An AGI, look at that, 10 to the negative 16th. That's virtually insoluble. That's such a ridiculously small amount that leaves. But you have to be careful because you can only use the KSPs to determine solubility comparisons when you have the same number of particles they break apart into. That's because the formula, this KSP, and this KSP are all going to be equal to x squared. So my x squared, my x is going to be proportional to this. But if one of them wasn't x squared, if one of them was 4x cubed, do you realize that my x value would not be in a direct relationship with the KSPs? Yeah. For example, let's take a look at these three right here. So if I take a look at CUS with a KSP of 8.5 times 10 to the negative 45, which, come on, man, right? AG2S of 10 to the negative 49, and BI2S3, 10 to the negative 73. Those are insane numbers, right? But you cannot compare these three KSPs by themselves and go, oh, wait a second. The KSP of CUS is the most soluble than these other two. Why? Because this breaks apart into an x squared. This breaks apart into a 4x cubed. Do you realize that this breaks apart into something ridiculous? Mm-hmm. So let's try this for a second here. Can you do me a favor? How much time do we have left in the class?
No time.
No time? Okay. So your mini homework assignment is going to be to solve for x for each of these three.
Okay.
And remember the assignment that I gave you before, the work from the textbook I told you wasn't due today? Yeah. That's going to be due Thursday. I'm hopefully going to be back for you on Thursday. If you think about it, just pray. I'm going back to the surgeon tomorrow, and hopefully she'll give me the all clear to get back because I am dying to be back there with you. But you'll also have that other worksheet, the titration worksheet. I will sign that off with you. So thank you so much. You guys are a wonderful group. I look forward to being back with you.
Bye.
Thanks, Kristen.